So we have seen how we can impart charge. Now, taking those concepts, we will go into the real world. These charges exert forces on each other. We have seen that. Like charges repel and unlike charges attract. Well, what is the force? What is the magnitude? What is the direction? That is governed by Coulomb's law. They exert forces on each other. Now, when you have a force, then work can be done. And if work can be done, then energy can be transferred. That's a real world. And when charges flow, we call it electric current. How do we make these charges flow? There has to be a force. And we will see that to create a force, basically we need what is called a potential difference. Potential difference creates force and drives those charges, making a current flow. And when a current flows, then work is done and energy is transferred. What is the direction of electric current? Well, if both positive and negative charges are free to flow around, then what is the direction? They will move in opposite directions. The direction of electric current is taken as the direction of the positive charges. That means if only electrons are moving, let us say, then the direction of current is opposite to the flow of the electrons. Now, in the real world, we have cells or batteries. They drive current. We will understand how does the cell drive current. Basically, how does it create a potential difference in the first place? And then, when a cell is providing power to a device like a bulb, it gets discharged. We can charge it back again if we have a particular type of cell like a secondary cell. So we'll talk of primary and secondary cells. Secondary cells are rechargeable like your mobile phone battery, and primary cells are not rechargeable like those dry cells that you see in torches. Welcome to the portals of what I call real learning as in really understanding what is happening in our real world. So don't skip and listen carefully right till the end. In the last session, we learnt about imparting charge by friction, by conduction, and by induction. And charges, they can exert forces on each other, either attractive or repulsive. Like charges repel, unlike charges attract. In this session, we are going to learn about what is the expression for that force, and we'll also learn about batteries. So if there are two charges here, Q1, Q2, suppose both of them are positive. They are some distance apart. Then they repel each other with a force F. The magnitude of the force is the same. This force F is the force exerted by Q2 on Q1, and this force is a force exerted by Q1 on Q2. They form Newtonian action-reaction pairs. So what is the magnitude of this force? It is proportional to the product of the charges and inversely proportional to the square of the separation between them. And the proportionality constant is called K. It is a constant, but it depends on the medium. So as long as the medium remains the same, then this K has got a certain value. You change the medium, that constant value will change. In SI units, this K has got a value 9 into 10 to the power 9, and units are Newton meter square per Coulomb square. How is that? If you take R square to the other side, it is force into R square, that is Newton into meter square. And then you have to divide this by Q1, Q2, that is charge into charge, that is Coulomb square. And this value is for vacuum or air. One major difference with gravitational force, although the structure is very similar for gravitational force, there's a constant G, then proportional to the product of the masses and inversely proportional to the square of the separation. The structure is very similar, but the difference is this capital G is called the universal gravitational constant. It doesn't depend on the medium. So the gravitational force is independent of the medium between them, but that is not so when we talk of electric force or electrostatic force. And you can imagine why, because any medium will contain electrons and protons. They will respond in some manner to the presence of charges outside. That is why this K depends on that medium. What are the characteristics of this force? It is also called Coulombic force or electrostatic force. First of all, this force is only applicable when the charges are at rest. If they are moving, then the question comes up, with what speed are they moving? If the speed is very large, let's say comparable to the speed of light, then a lot of changes have to be done. So that is why this is about electrostatics, that is, charges are at rest. One is this force is along the line joining the two charges. And what is the direction? It will be away. Force will be repulsive, that is away, outwards, as I've shown here, repulsive if the charges are similar, either both positive or both negative. And attractive, that means towards each other, if they are dissimilar, that is, one is positive and the other is negative. However, the magnitude of this force is only based on this formula. And you can see that this formula takes care of the direction also. See here, if Q1, Q2 are both positive or both negative, then this force has got a certain direction, right sign. If one of them is negative, then this quantity on the right hand side becomes negative. That means the force direction has to be reversed. The force by charge 1 on charge 2 is equal and opposite to that by charge 2 on charge 1. These are Newtonian action reaction pairs. Importantly, this obeys a superposition principle. That is, force on a given charge due to many charges around it can be found by simply adding up vectorially the forces exerted on that given charge by all the other charges superimposed on each other. But the addition has to be a vector summation, not a scalar sum, because force is a vector. Right? So this is a very, very important Coulomb's law. Another thing that must be mentioned here, that this law only applies when these are so-called point charges. The charges are sitting on particles which are very small. What is very small, or how small is small? That is when the size of that particle on which the charge is sitting is small compared to the distance between the charges. That is when we can approximate it to a point charge. This won't apply directly if you have two bodies of reasonable size and they have got some charges on them distributed in some manner. Then what is that R? How do you decide that R? Then a lot of additional things come up, which is called integration, but we are not getting into that. So Coulomb's law applies only to point charges. Let us practice this superposition principle. There are three charges, 4 Coulomb, 2 Coulomb, and minus 2 Coulomb. What is the force on the 2 Coulomb charge, the net force on the 2 Coulomb charge? Due to the 4 Coulomb charge, there will be a force which will be repulsive. Let us call it F1. Due to the minus 2 Coulomb charge, it will be an attractive force. Therefore, the direction is the same. Let us call it F2. The directions are the same. So the addition becomes very simple. The net force will be in the same direction, and the magnitude of this force will be equal to the magnitude of F1 plus the magnitude of F2. In this case, the directions are the same, so no problem. So let's write F1. K, I will replace the value of K later. K, Q1, I'm only writing the magnitude. Direction is already decided. Q1, Q2 divided by R square, that is 1 square. So that is 8K. F2, K, Q1, Q2. I'm only writing the magnitude divided by the separation is 2, so 2 square. So that is only K. So therefore, the net force is equal to 9K. Very simple question. What happens if we have a different configuration? We have an equilateral triangle of side 2M, and on each of the vertices, some charges are sitting. What is the net force on this 2 Coulomb charge? Now, they're all positive charges, so on this 2 Coulomb charge, there will be a repulsive force F1 by this 4 Coulomb charge, and by the other 4 Coulomb charge, it will be a repulsive force, let's call it F2. The two forces are not in the same direction. Although the magnitude is the same because 4 and 2, 4 and 2 charges are the same and the separation is also the same. So magnitude of F1 is equal to the magnitude of F2. So I'll write like this: magnitude of F1 vector is equal to the magnitude of F2 vector, and that is equal to K Q1 Q2 divided by R square. So that is 2K. So a 2K force works here, and a 2K force is acting like this. We have to add these two forces factorially. We can add it in various ways. One is complete the parallelogram based on these two lines, and the resultant of this summation is the diagonal starting from the same point. Now, angle we know, this is equilateral triangle, so all angles are 60 degrees. Therefore, this angle is also 60 degrees, and we can always find what is the length of the diagonal of the parallelogram. That will be the magnitude. We can do it in another manner, that is, take components. Now, if I extend this line, then this angle is 30 degrees, this angle is 30 degrees, right? So the component of this F1 in this direction, this angle is 30, so this is 60. The component of F1 in this direction is F1 cos 60. And the component of F1 along that direction is F1 sin 60. Similarly, for F2, the component in this direction is F2 cos 60, and the component in this direction is F2 sin 60. We have taken the components. Now add these vectors. These two vectors are equal and opposite. The magnitude of F1 is the same as that of F2. So these two cancel out and these two add up. So the net force is in this direction, and the magnitude of the net force is 2 times F1 sin 60. And F1 is, the value is 2K, and sin 60 is root 3 by 2. That means it is 2 root 3 into K. We can substitute the value of K, 9 into 10 to the power 9, and the whole thing will be in newtons. The direction is upwards. This is also another example of superposition. So you'll find many such questions in your assignment and in the school textbook about various configurations of charges, and you have to find the net force on a particular charge. So that was electrostatics. Charges at rest. Now let's talk of charges in motion. We have talked about lightning, so this is also moving charge. It is a giant spark between the cloud and the earth. Charges in motion play a very important role. And then we define a quantity called electrical current. Electrical current. Let us start with some analogies. You have a fast flowing river. and we'll say, don't go inside the river. The current is very strong. The current of the water is very strong. What do we actually mean by that? That the speed is very high, right? But we can also state it in another manner. Suppose I imagine a rectangular frame like this, perpendicular to the direction of the flow of the water, and then ask the question, how much water passes through this frame per second? The answer would depend on what is the area of this frame. Larger the area, larger the amount of water flowing per second. Second is the speed of the water. So ultimately, we are talking about amount of water crossing that frame per second. Similarly, if you talk of heat current, heat is flowing from this hot side to the cold side. How much heat is crossing a particular cross section per second would be heat current. So when you talk of electrical current, we talk of how much charge is flowing per second through a particular line or through a particular cross section or through a particular point, depending on the scenario. This iron rod is like, let's say, a cylindrical rod. So let me draw the cylindrical rod like this. And some current is flowing through this, okay? The measurement of current would be, I take a cross section of some size, either the entire cross section or a small cross section, and perpendicular to that cross section, how much is the charge Q flowing per second? That would be the current over there. Or if I have another configuration, I have an area only, like a rectangular plate. The thickness of this plate is negligible. Actually, everything has got volume. Everything, every material has got some volume. But here we'll approximate it to a plane only because the thickness is negligible. And some current is flowing, let us say like this. Then the measurement of current would be, you draw a line perpendicular to the direction of the charges and again ask how much current is flowing per second through it. Or it could be a thin wire where there's no area, and then we'll only say what is the amount of charge flowing through this particular point now. So it depends on the scenario. But essentially, current is about amount of charge flowing per second. We denote moving charges or electrical current as the symbol I. Current is a rate of flow of charge across a cross section. If I take a volume like a cylinder, the rate of flow of charge across a cross section, that means how much charge is flowing per second, rate of flow of charge, how much charge is flowing per second across that cross section. And that cross section should be normal to the direction of flow of current. If current is flowing like this, then don't take an area like this. Take an area that is perpendicular to it and then ask how much is flowing. So if a charge Q crosses a cross section in time t, then the current is I charge upon time. That is Coulomb per second. And Coulomb per second is given a name called ampere. The SI unit of current is called ampere. And by the way, since I took a large time interval, this current would be the average current in that time interval. Instantaneous current would be taken when this time interval is taken to be very small. Very importantly, current is a scalar quantity, not a vector quantity. Current has got direction, current has got magnitude, but it's still not a vector. You see, for a quantity to be classified as a vector, it is necessary that it has got a magnitude and direction, but that is not sufficient. It is not sufficient. Sufficiency comes in when two such vectors can be added as per the vector law, which is the parallelogram law. But current doesn't obey any such rule, number one. Number two, what is the direction of current also? It depends on the shape of your wires. Suppose the current is flowing from a point A to the point B and the wire is straight. So you can say, oh, this is the direction of the current. But suppose the wire is like this, then the current is like this at this particular point, like this at some other point. A vector has got a unique direction in space at a certain position and at a certain time. But here it changes. So there's no direction as such. That way we can talk even in terms of time having a direction. Yesterday is to my left and tomorrow is to my right. We can conceptualize time like that and say time is flowing like this. No, time is a scalar quantity. So the unit of current is ampere, written as A. And by the way, this is one of the seven fundamental quantities in physics. So 1 ampere current will be 1 coulomb per second, crossing a particular point or a particular cross section or a particular line. That is correct. Question is, how do we make charges flow? And what is the advantage in getting them to flow around? We will see that. But let's first classify direct current and alternating current. Direct current DC is a current that doesn't change direction, but alternating current AC is something that changes direction. So here are examples of direct current. I'm plotting current versus time. It can be a constant current or it can be a varying current like this red one, or it could be some other current which is changing in magnitude in some random manner, but you can see it is all the time positive. Current is not changing direction, so it's all DC. We can call this current as constant DC, and the other, this one we could say pulsating DC. All DC only, they are not changing the direction. But alternating is current versus time. You see, we could have a perfect sinusoidal curve like the yellow one. Sometimes it is positive, sometimes it is negative, or it could be this square kind of a wave. Again, sometimes it is positive, sometimes negative, or it could be this blue one which is following some random shape. But current is changing direction, that is called alternating. When you have a DC source, we show it like this. Since it only goes in one direction, doesn't change direction, we say this is a positive terminal and this is a negative terminal, and current will flow out from this source. This is a DC source, will flow out of this and pass through some circuit and then come back into the negative. For an AC source, we can't assign a permanent positive and negative sign to these two terminals. So we just show it with a curve like this. That is a symbol for an AC source. If you look at a battery, your mobile phone battery, for instance, it provides DC. Whereas you use generators at home when there's a power cut, you use generators, they provide AC current. In our homes, in our plugs, we get AC current, not DC current. There are various reasons for that, why we chose AC. Now, current flow. We can create positively and negatively charged bodies by friction, induction, or conduction. If you look at a metal, and that is a primary focus in this chapter, there are lots of free electrons. Typically, the outermost electron in that atom, since it is loosely attracted to the nucleus, on acquiring thermal energy due to the room temperature, it gets sufficient energy to leave the parent atom, but not sufficient energy to leave the entire body as such. So after leaving, what does it do? It has got thermal energy, so it will move around, but in which direction? There is no preferred direction. So all these electrons would be moving around randomly. And by the way, this density of free electrons is very huge. Per cubic meter or even per cubic centimeter, it would be in billions. We say that there's a large ocean of free or mobile electrons. In fact, that is why metals are good conductors because they have got mobile charges. Now, if there's a metallic body which we say is positively charged, there are no mobile positive charges in a metal. It is only electrons that are mobile. But if you say that a metallic body is positively charged, we can interpret it as having a deficit of electrons. If you take out electrons, it becomes positively charged. And negatively charged bodies have an excess of electrons. So in a metal, only electrons are the free or mobile charges. But there are other materials, for example, in electrolytes and in acids, we can find positive as well as negative charges which are free to move around. So what is the current direction? See this picture. I have a positively charged body and a negatively charged body. If I connect them up, then there's a potential difference between them and charges move due to the potential difference. We can interpret it here as since it is the electrons that are free to move around, both of them are metals, only electrons can move around. The right body has got an excess of electrons and that moves towards the left body, which has got a deficit of electrons. But be very clear, charges flow due to a potential difference. Let's do a small question. Suppose n electrons go through a cross section in time t. What is the current? N electrons. Each electron has got a charge 1.6 into 10 to the power minus 19. So the total charge that crosses is n times the charge on each electron. That means n times this number divided by the time. That is the time taken. Now, if both positive and negative charges are moving, then what is the current direction? So we have to adopt one direction. You see, if a positive charge is moving this way and a negative charge is moving this way, we cannot say that there's no current. We cannot say that there's no current. Charges are moving, no? As long as they are moving, there is a current. The current will be actually a summation of the two. So therefore, we decide that direction of current will be taken as the direction of the flow of positive charge only. And if both of them are moving, then the current due to this negative charge is also taken in this direction. So therefore, in a metallic wire, only electrons are flowing. If electrons are going from here to here, right, then the current will be taken as moving from here to here. We have to choose one convention. So in a metal, the current is in the reverse direction of the flow of electrons. We must understand this very clearly that flow of negative charge from A to B is equivalent to an equal positive charge moving from B to A. That is why this convention. See, I'll prove this right now. A has got a charge minus 2 Coulomb, B has got a charge of plus 10 Coulomb to start with. Suppose A donates minus 1 Coulomb charge to B, then what is the situation of A and B after this transfer? How much charge is left on A? It had minus 2, minus 1 has gone, so A is left with minus 1 Coulomb. As far as B is concerned, it had plus 10, now it is receiving minus 1. Charges can be added algebraically. So plus 10 and minus 1 added together gives us 9 coulombs. So the result of this charge transfer is B is left with 9 coulomb and A is left with minus 1 coulomb. This was transfer of minus 1 coulomb negative charge from A to B. If I take positive charge of 1 coulomb to go from B to A, then what is the result? B had plus 10, it has donated one of them to A, so it is left with only 9 coulomb. A had minus 2, it is receiving plus 1, add them up algebraically, minus 2 plus 1 is minus 3. So you can see here that in the end, the result is the same whether minus 1 coulomb goes from here to here or plus 1 coulomb goes from here to here. They are equivalent. So therefore, if I have a constant stream of electrons going this way, it is as good as saying that equal amount of positive charge is going this way. That is why we take the direction of flow of current as opposite to the direction of flow of electrons. And if both positive and negative charges are moving, simply add, don't subtract. When both types of charges are free to move, and they will move when the reason is provided, that is potential difference is provided, they will move in opposite directions. When you apply a potential difference between 2 points, charges will move. And if both types of charges are there to move around, then they will move in opposite directions. The current due to each charge adds up. So, if you talk of metals, the electrons go in this direction, the current is taken like this. If you take an electrolyte or an acid, the positive charge and negative charges will always move in opposite directions. So the current is taken as the flow of direction of positive charge. So the contribution from this guy and the contribution of this guy is actually added up, not subtracted. So current is not zero. Is that clear? I hope so. Now, who will provide the potential difference? This word potential we have been talking about, and we are going to go a lot deeper into the concept of potential and potential difference. We already know about potential energy, the concept of potential energy. In the case of gravity, we talked about it, for instance. That same concept applies here also. And potential energy are intimately linked. Right now, let's just say that a cell provides potential difference. This is a very familiar so-called dry cell. There's the brass cap, which is the positive terminal, and the zinc base below is a negative terminal. If you connect up between the positive and negative, a load, electrical load, is called load in electrical engineering. Like a bulb, if you connect it up, then the bulb glows. So, negative terminal, you're providing a path basically through the bulb. Negative terminal has an excess of electrons and positive terminals has got a deficit of electrons. You have provided a path. You can imagine a deficit of electrons means positive charge. So as you know, negative charges are attracted to the positive charge. So electrons from here will rush through this wire into the positive charge. So electrons are flowing from the negative terminal to the positive terminal, and as per our convention, the current is from positive to negative. As long as the current is flowing to the bulb is glowing. And the symbol for this battery is like this, plus minus. I use the word cell here, and I also said battery. There's a slight difference between the two. Cell is a single source of potential difference like this. If I combine many cells together in some form, it forms a battery. But we're not very strict about the usage. The word cell and the word battery are sometimes used interchangeably. But strictly speaking, a battery is a group of cells. The structure of this thing inside, if you open up, it is basically zinc in ammonium chloride. Essentially, that is there. There are many other things. The carbon rod, which acts like an electrode. The zinc can is an electrode. The metal bottom is the negative terminal. And here's a metal top, which is a positive terminal. The battery maintains a constant potential difference between the positive terminal and the negative terminal. It maintains a constant potential difference. How does it do that? By chemical action, completely by chemical action. In a cell, chemical energy is stored. And when you connect it up to a load, like a bulb or a fan or whatever, then that chemical energy is converted into electrical energy by sending current within that circuit. So when a battery is supplying current to a load, it is converting its stored chemical energy into electrical energy. As you know, energy can't be created or destroyed. We can only transform energy from one form to the other. That's what it does. So there will always be chemistry involved in batteries, and there are various types of batteries now. This is called the dry cell. Your mobile phone battery is different, lithium ion. The car battery is different, it is lead acid. But basically, there is chemistry involved. And due to chemical action, the battery maintains a constant potential difference, which is what drives the charge. Current flows due to a potential difference. Now, there are two kinds of cells, primary cell and secondary cell. Secondary cell is also called accumulator. What is a primary cell? It is not rechargeable. The one that I showed you just now is not rechargeable. When it is supplying current to the load, it is discharging in the process. It will take a few hours to discharge, but ultimately it discharges. And after that, you have to throw it away and buy a new one. Why? It is converting its chemical energy into electrical. There is a chemical reaction involved. So, as you know, in chemistry, some reactions are reversible, some are not. In the dry cell example, the reaction is irreversible. So, because it's irreversible, we have to just throw it away. So, dry cell, Leclancher cell, Daniell cell, voltaic cell, they are all primary or not rechargeable. But secondary is rechargeable, like your mobile phone battery. Because of the chemistry involved here, the chemical reaction involved is reversible. It is a reversible thing, like lead acid accumulator used in cars or nickel ion lithium hydrogen used in mobile phones is also called lithium ion batteries. There's a lot of research going on these days to come up with better and better batteries that can provide current for a longer time, which can get recharged in a very short time. And that research is going on because we want to produce better and better electric cars instead of petrol cars. So this is a car battery, very heavy because it contains lead. This is a mobile phone battery, lithium ion. This is also your mobile phone battery. And you know, you have this adapter. When your battery of the phone is nearly discharged, then what do? Simply connect up this adapter to the plug, and the phone gets recharged in a few hours. We are basically reversing the chemical reaction. So a cell is just one single thing. A battery is a group of cells. So you can typically connect it in many ways. This is a connection in series. This is a cell. The positive of this is connected to the negative of the next one. The positive of this is connected to the negative of the next one, like that. So if the potential difference between these two terminals is V and I connect three identical cells, then the potential difference between this end and this end will become 3 times V. So we can increase the potential difference by combining cells and forming a battery. So this is a cell, it is supplying current to this bulb, which is a load, and there's a switch. When you close the switch, it's a kind of plug switch. This means when I put this dot here, it means the switch is closed and then the current flows. When the cell is supplying current, it discharges over time. And for the current to flow, there must be a closed loop. Otherwise, current won't flow. If I want to recharge our battery, which is rechargeable, then you see what we do. That power bank or adapter, whatever we have, we connect in such a way that the current flows into the battery like this and comes out. That means inside the battery, it is flowing from positive to negative. This is positive, this is negative. This is while charging. While discharging, you see what is happening. Outside, it is flowing from positive to negative. Inside, it is flowing from negative to positive. That is when it is discharging. To reverse the chemical reaction, we have to pass a current in exactly the opposite direction. That is how it is done. So, to conclude this session, let us summarize primary cell versus secondary cell. Primary is not rechargeable and secondary is rechargeable. That is a basic difference. And that happens because the chemical reaction involved is irreversible. Here it is reversible. Chemical energy is converted into electrical energy when the current is drawn from the cell, that is, the cell is supplying current. And there's no question of charging a primary cell, but secondary cell we can charge. The reverse process is done, that is, we are supplying electrical energy and that reconverts into chemical energy by the reversible chemical reaction. There is a concept of resistance. Larger the resistance, smaller the current. We'll talk about the concept of resistance also. But since we are making a complete table, I'm mentioning it here. Every cell has got an internal resistance. Its internal resistance is high, but for a secondary cell, it is low. And that's a good thing. For a cell to have a low internal resistance is a good thing. The primary cell can provide us only small currents or weak currents, but the secondary cell can provide us anything, low or high current. This primary cell is light and inexpensive. This dry cell is a few rupees, but it is use and throw. Whereas the rechargeable mobile phone battery is a few thousands, maybe 2000, something like that. So it is expensive and it is also much heavier. Examples we talked about. Examples we talked about. That is a summary. So in the next session, we are going to see how these cells are supplying current, what happens really, because think about it, when the cell is supplying current to a bulb, the bulb is glowing, it is radiating light energy. It is radiating light energy. From where is it getting that energy? Battery is supplying it. We'll talk about that. That's very interesting.